The title here is Joint Decoding of Trained Transduction Models for Sentence Compression. And the authors, none of them get a visa to come here to present their work. Therefore, their work is presented by me. I'm Kai Zhang, and some of you may come to my presentation on the 26th about grammar correction. And in fact, the task here is, you can see from the title that the task here is sentence compression. And the methods we use is trained transduction models. And the problem lies in the joint decoding because it's complex. And the paper is mainly about how to efficiently do the joint decoding. And in fact, before yesterday, I'm new to the task about sentence compression. But after a day of difficulty reading the paper, I think I found a relatively wonderful way to do the sentence compression task. So let's explore it together. So first is the outline. We assume that some of you are also unfamiliar with the task of sentence compression. So we first give an introduction of the task, then give our motivation to, that is decoding the trained transduction model augmented with language model scores. And the joint decoding is the main part of the paper, and we'll describe the components and algorithms to efficiently decode the result. And the experiments and results and some later discussions will be listed in the last part. So let's begin. The task of sentence compression is task of producing a summary of the single sentence. Well, the produced sentence should have the four properties. The first is in the compressed sentence, they should use less words than the original sentence. And you should preserve the most important information, and the compressed sentence should also be grammatical. And sometimes the last one, the reordering, deletion, or substitution is needed, just like machine translation. And from the properties, we can intuitively think of one kind of method called the deletion-based sentence compression method, which tries to delete a subset of words from the original sentence to get the compressed one. So maybe you should preserve the important words and delete the unimportant words, and then guarantee that the remaining structure is also grammatical. So I'll give an example here. The source sentence, the long one is Prime Minister telling Blair. This is the case for holding terrorism suspects without trials was absolutely compelling as the government published new legislation allowing detention for 90 days without charge. Well, as a Chinese, I found it difficult for me to get a clear understanding of this paragraph at first reading. But if I look into the target, Blair insists the case for holding terrorism suspects without trial was compelling. Well, this sounds reasonable to me much more. So you can see that the unimportant words are deleted and the structure of the sentence is not changed, and the compressed sentence is also grammatical. So this is the task and the method. And in previous works, like the pioneer work is Knight and Markio 2000, they use a noisy channel model, which is a generative model, and the decision tree, which is a discriminative model, which use this kind of method to do the compression work. And later in 2006, McDonald proposed a structured discriminative model, which tried to design features on the compressed sentence and their relation to the original characters based on some linear classifiers. And this showed good results. And later in 2008, the constraints-based models play an important role in the task, and the IRP-based method and first-order Markov logic method in Huang also plays an important role. Like because in IRP, you know, some of the global constraints can be made to get a globally optimized result. And it was not until the recent years that the tree transduction models that play an important role in this task, and the Conda-Lapad promotes two methods for the trained transduction model-based sentence compression method. In fact, our method here is also using the concepts from the train transduction models, and I'll mainly explain it in the following slides. So what is the compression as a tree transduction method? And I give example. There are two path trees in the above, and on the left it is the source sentence, and on the right is the target sentence. We can find a map from the source tree to the destination tree. Like in here, we link the RB into empty set and this WP to this WP. Yeah. So this is the example of the tree transduction method, and the image is taken from Kai and Lepard. We focus on the synchronous tree substitution grammar in this work, and usually in the data of training a reasonable transduction model, we need to align the trees. In fact, it's in all the training data, there's only the alignment between one sentence to another. I mean the original sentence to the compressed one. There is no alignment on the trees. But the alignment in this task is not that difficult compared to machine translation, because in machine translation, you may need to consider the reordering problem, but here we do not need to consider order, and it's relatively easy to align the trees using some heuristic rules. And this image is also taken from that paper of Lepard. And so you can think of the training part is relatively easy to solve, because you can just learn the rule with W based on some classifier like the structure SVM in our paper. And the remaining problem is the decoding problem, which given the weight of the rules, and you find the best derivation. A derivation means the compressed sentence. So in 2009, Kai and Lepard proposed a scoring function, which in his experiment showed that this scoring function is good enough for sentence compression. You can see that this scoring function is composed of two parts. The first part is the weight sum of features on the transduction rules, the derivation rules. And the second part, the log p n-gram y. This is the language model score. That means that compared to the discriminating, compared to using the tree transduction model only, we add an extra language model score for the scoring function. And because we add this extra term, the exact decoding becomes intractable. And in their work, they use the beam search instead of get the exact result. So we take a closer observation of the scoring function. Well, this scoring function is made up of two parts. The first part is the weighted sum of features, which comes from the derivation rules. And the second part comes from the language model source. And in fact, either part can be used alone as a sentence compressor. Therefore, we just omit the last part and see the first part, only the transduction rule part. So this part can factorize over rules, just like you do parsing. Yeah. So you can efficiently use dynamic programming to do the decoding. And for details of how to use dynamic programming to do the decoding, you can refer to the paper of Kai and Lepard 2007. And this is the first part. If we do not consider the first part, only consider the language model part. In fact, it's still can factorize over n-grams. Well, let's try it easy. If you factorize over n-grams, like from character to character, from left to right, then you can also easily do the decoding by dynamic programming. And but in this time, the length should be specified to avoid the trivial solution, because it's a log of probability. Therefore, they do not favor the sentences with longer length. So this is a very naive compressor. And if we view this as an n-gram factorized equation, and then we can integrate some rich features. Well, if we integrate some rich features, we can result in the similar form of the scoring function, just as McDonald 2006 in this paper. Like there is a combination of features on the n-grams. Here, Z means the compressed sentence, and actually the original sentence. And you can design features on Z. And the function L means it maps the character in the compressed sentence to the original one. And you can design features based on the character sequence. Well, this is quite similar to the method proposed in the McDonald 2006. And now, if we do not view them individually, we come together as our scoring function in the paper. We can find that either part can factorize over some local structures. The first part factorize over the transduction rules, and the second part factorize over the n-grams. So either part can factorize over local structures. But if we put them together, they factorize over different kinds of structures. So how to do the dynamic programming? Maybe you can build a large dynamic programming table, but in this case, time complexity is also very high. It's near the exponent, and that's why in the paper of Cohen and Lapada 2009, they conduct beam search, and they decide not to find the exact result. And so the problem lies in the joint decoding. So how to solve it? How can we utilize the efficient decoding of either part of either part independently? One answer is the Dow decomposition. Well, for the details of Dow decomposition, you can refer to the Rush and Collins 2012 details of because it's a very complex method, I cannot list them all in this slide alone. Well, basically, you can think of the method as that. The GY means the factorized over transduction rule part, and the FZ means the factorization over the language model part. And you can think of Y and Z as the indicator of which character should be kept in the compressed sentence. And we may give some constraints of the score function that we require that if you keep some character using the transduction rules, then you should also keep the same character of the language model part. Therefore, you can add the scores together. So through the Lagrange method, you can build a star objective, and this can be two independent decodable parts. In fact, this is the basic idea from the Dow decomposition algorithm. You can refer to this paper, and this is the decomposition based on this task. And also the algorithm for the joint decoding is listed as below. And I think you may refer to the original thing I mentioned before to get a clear understanding of why this works. But I should mention that this one, the third line, the argmax and argmax here all can be solved through dynamic programming efficiently. So therefore, the whole algorithm can run efficiently. So, so about the experiments, we use the data sets the same with Cohen and Lapad, and we refer to as written and spoken because the data comes from the written news and some broadcast we call the spoken part. And we use baselines, the pure tree transaction, which is part of our method, and the structure discriminant model, which is the other part of our method, because we extend the language model with rich features to be the structure discriminative models. And also we use T3 and the language model score with beam search solution, which is used in 2009. And also method by Glanis 2010, which is a two-step max-int. So the evaluation is also the same with the previous works used in Clark and Lampard 2006, and also the manual rating is used from the grammatical aspect and the importance reservation aspect. And we also control the compression ratio of the different systems to be similar. So here is the result, and above is a state-of method and its comparison, and this is a beam search, which we should refer to in the 2009 work, and this is the DAO decomposition, and our result, you can see that our result outperformed the previous ones, both in the written and in the spoken data set. This is the automatic matrix. And also for manual ratings, our method can also outperform the previous ones. And in fact, the tree transduction part tries to measure the global syntactic integrity. And the language model scores, because language model scores are built on the compressed one, compressed sentences. Therefore, it can measure the local smoothness, and structured discriminative models is an extension of the language model, and therefore it also measures the local smoothness and the joint decoding combined power. And I'll give several examples, and I don't have enough time. And in summary, this is the task is the sentence compression, and the method we use is train transduction rules, and what we focus on is the joint, how to make an efficient joint decoding of this task. And thank you all. And if you have any questions, please contact the author. Thank you.
So yes, indeed, probably asking a question might not be fair, but if somebody has a comment, or if there are no comments, then perhaps thank you very much again.
Thank you.